Morning, students. So we'll be discussing the topic code optimization. So in code optimization, we have seen certain constructs such as syntax tree, directed acyclic graph, parse tree. So let us have a quick review of these. So what is a syntax tree? Syntax tree is similar to parse tree. But what is the difference between syntax tree and parse tree? In syntax tree, the extraneous nodes are removed. So it is a good representation closer to source language, and it is used in application like source to source translation, syntax directed editor, etc. So we will see one example. What is a syntax tree? So some example expression is given: a asterisk a plus a asterisk b plus a asterisk b. Then it is added with a asterisk a. So the syntax tree corresponding to this expression will look like this. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 nodes, leaf nodes are there. So A asterisk A is evaluated, then A asterisk B is evaluated. First expression, then second sub expression A asterisk B, they both are added. So this is the value. This value node is representing A asterisk A. This node is representing A asterisk B. So they both are added. So this node is representing actually A asterisk A plus A asterisk B. Now next is A asterisk B. So A asterisk B, this node is representing A asterisk B, and this node is representing A asterisk A. So A asterisk B is also added. So this A asterisk B is added to the previous expression A asterisk A plus A asterisk B, and finally this is also added. A asterisk A is added to the previous expression. So this is the syntax tree corresponding to this particular expression. Now, what is a DAG, directed acyclic graph? It is a acyclic graph having no cycle. So it represents an improved syntax tree where subtree duplications such as common sub-expressions are identified and eliminated. So we have same, you can say, expression for which we are trying to create a DAG. So in this, we all know the rules and regulation how to create DAG. So A node is created for A, then A asterisk A. So already we have created a node corresponding to A, so no need to create a new node. So this A is, you can say, used with A by this operator. So this node is representing A asterisk A. Next is A asterisk B. So this is B. So this A and B is joined with this operator representing A asterisk B. Now this A asterisk A is added with this A asterisk B. So this is the result of A asterisk A. This node is representing A asterisk B. So they both are added. So this node is representing this expression A asterisk A plus A asterisk B. Next expression is A asterisk B is again added. So to this node, the value of this node is again added. So this node is representing A asterisk A plus A asterisk B plus A asterisk B. Now to this node, which is representing addition of three sub expression, we have to add A asterisk A, and this node is representing A asterisk A. So we will add A asterisk A to this. So this node is finally representing the DAG of this expression. Now next kind of optimization is peephole optimization. So what is peephole optimization? Peephole optimization is a code optimization performed on small part of the code. So this is actually optimization performed on very small set of instruction in the code segment. The small set of instructions or small part of the code on which p-hole optimization is performed is known as p-hole or window. It basically works on the theory of replacement in which a part of code is replaced by shorter and faster code without changing its output. And p-hole optimization is a machine dependent optimization. The objective involved in p-hole optimizations are to improve the performance, to reduce the memory footprint, to reduce the code size. So what are the techniques involved in p-hole optimization? Number one technique is redundant load and store information. So in this technique, the redundancy, whatever redundancy is there, it is eliminated. So for example, we have a code in which the 5 instructions are there. So y equals to x plus 5, I equals to y, z equals to y, w equals to z asterisk 3. So this is the code before optimization. And when compiler optimizer optimize the code, so if you observe this, I equals to y and value of I is assigned to z. So this is sort of copy propagation. So the value of z will be removed by the optimizer. Code will become y equals to x plus y as it is first instruction. Second instruction is I equals to y, no change. But this third instruction gets removed. And instead of z, what compiler will use later on, it uses I. So the last instruction will be w equals to y asterisk 3. So instead of z, optimizer replace it by the value y. Second technique is constant folding. So this constant folding, as I told you earlier, the code that can be simplified by user itself is simplified. So the code, suppose the source code is having this statement x is equals to 2 asterisk 3. So optimized code will be x equals to 3. So this expression is evaluated and its value is computed, and that computed value is assigned to x. So at runtime, this will take less time because asterisk otherwise would take some time in order to execute. Strength reduction. Third technique is strength reduction. So operators that consume higher execution times are replaced by the operator consuming less execution time. So we know that in any language there are different types of operators available, and their you can say cost is different. So we all know asterisk operator is costly as compared to addition or subtraction. Why? Because uh, the cost involved while evaluating the asterisk multiplication operator is more as compared to addition or subtraction. So suppose in your code you are using this type of instruction y equals to x multiplied by 2. So x multiplied by 2 can be replaced by optimize instruction such as y equals to x plus x. So here asterisk is used as operator, here addition is used, and we know that addition is the, you can say, cheaper operation as compared to multiplication. Or you may have this code y equals to x divided by 2. So this code can be replaced by the optimizer y equals to x right shift by 1. So we know what is the meaning of this shift. Next technique you can say is null sequences. So in null sequences, useless operations are deleted. If you have some useless operations available in your code, that is to be, you can say, removed. Next technique is combined operations. Several operations are replaced by a single equivalent operation. So this is some of the techniques in p-hole optimization. Thank you. This is all from my side.